Okay, good morning, guys. Last section here we're going to be doing, we're going to be L'Hopital's rule, but I like this problem because this is a problem from the actual AP test 2016. It was multiple choice, so of course you did have some choices of answers, but it was non-calculator, and it is a related rates, just to see they can put a different twist on things. And this one says, sand is deposited in a pile with a circular base. Circular base. The volume V of the pile is given by the volume equals radius cubed divided by 3, where R is the radius of the base in feet. Okay? The circumference of the base, now they're switching gears. I see no circumference in here. The circumference of the base is increasing at a constant rate of 5 pi cubic feet per hour. So that is kind of telling me dc dt equals 5 pi feet per hour. It's not kind of telling me that, it's telling me exactly that. Okay? And they want to know, when is the circumference, or no. It's increasing at a constant rate of 5 pi feet per hour when the circumference, of the base equals 8 pi feet. And they want to know what is the rate of change of the volume. So find dV dt of the pile in cubic feet per hour. Okay, well, they want me to find dV dt. Well, how the heck am I going to do that? Find dV dt. When the circumference is changing and I have a particular circumference, well, what do I know? I know the volume of my pile is going to be 1/3 R cubed. Okay? I know that's the volume of my pile. What else do I know? I also know if I take the derivative of this thing right here, right now, what's going to happen is I'm going to have a dV dt and a dr dt, and I know nothing about dV dt. That's what I'm trying to find, and I know nothing about dr dt. So I need to kind of think about a second here, and remember, this is non-calculator. I need to think, how the heck, because I have a rate of change of circumference, how the heck, and I have a radius here, how am I going to relate the circumference and the radius? Well, doesn't circumference equal 2 pi r? Okay? So if I'm looking here and I'm thinking, well, if I came over here and I took the derivative of this, right, I'm going to get dV dt equals 3 times 1/3 is gone, so I have r squared dr dt. Okay? And I have a related rates equation that I can plug squat into. Okay? But I do know I'm looking for, I have the rate of change of circumference here. So if I came over here and I took the derivative of my circumference, I get dc dt equals 2 pi dr dt, right? So I can solve, they gave me information to find dr dt. So I know dc dt, this is going to be 5 pi equals 2 pi times dr dt. And notice, they didn't give me my circumference. They're expecting me to know this one. Well, it's such a basic one. I know dr dt, hey, that's going to basically equal 5/2, isn't it? So I have one variable I can plug in over here. So I know this is going to be 5/2. I need to find out what dV dt is. So that means I need to figure out what the heck is my radius. Well, how am I going to do that? Well, I do know my circumference. This is my moment in time. So I do know my moment in time when the circumference is 8 pi. I know that's going to equal 2 pi times the radius. So at my moment in time, my radius is going to equal 4 feet, isn't it? So now that I know that's going to be 4 feet, I'm going to plug this over here, and I'm going to square it. And I'm going to come along, and I'm going to say, hey, dv dt equals, well, I'm going to rewrite that as times 16 over 1, and I can reduce that and say that's going to be 40. And because it's a rate of change of volume, it's going to be feet cubed per hour. Okay? Feet cubed per hour. And that's how I would have to find dv dt. It's just a little different spin, okay, on the problem. No, this one was not in your note sheet. Sorry, I should have said that right away. It was just an extra thing that I came up with that I found, through a little digging. And it's just another application that all related rates, they're not always going to be free response problems. They will nest a few in multiple choice, okay? And obviously, this is going to be one of your 5 potential answers on the bottom, okay? Just a different spin on it. So if you didn't catch that, you might want to rewind it and watch it again. Well, what we're doing here is we're jumping forward into 8.2. This is called L'Hopital's rule for limits. Now, why are we doing this now? Because this is our final application of limits that we're going to be doing, okay? And I'm going to do the whole thing today. And what we're going to do is recall the following limits, okay? So L'Hopital's limits, this is a rule for when we get indeterminate forms of 0 over 0 or in any form of infinity over infinity. So recall limits back in chapter 2 when we first started doing limits. Well, if we tried substitution, which is what we always should try first, if we try substitution in here, we know this limit, when I plug a 1, it's going to give me a 0 over 0. And what did that tell us? That told us, hey guys, you need to work a little bit harder. We know there's a hole in the function here, but 0 over 0 specifically told us the limit exists, go find it. And if I did my sine x over x, well, if you forgot what that limit is as I approach 0, well, the sine of 0 is 0 over 0. That was that fun one. Well, that was the one we had memorized was 1. And if I look at this last one, the limit as x approaches 0 of 1 minus cosine x over x. Well, cosine of 0 is 1, so I get 1 minus 1 in the numerator, or 0 over 0. And all of these produce the indeterminate form of 0. Well, if I think about this, as I have written here, okay, the first limit we found algebraically. Okay, we saw we had a factor of x minus 1 living somewhere in the numerator, so we factored the top, we factored the bottom, we reduced out that common factor of x minus 1, and we reduced it out, and we redefined our function, and then we reevaluated our limit, okay? The second two of them here, okay, well, the second two, we needed to use graphing methods to get those because there really wasn't a great algebraic method to get those. However, there are many indeterminate forms for which algebraic nor non-geometric methods will produce a limit, meaning we can run into limits like here that we cannot algebraically manipulate easy, and they're a bugger. And you know when these limits are going to produce themselves? They're going to be on the non-calculator part of the AP exam because they don't want you to graph them and find the limit. They want you to know how to apply L'Hopital's rule. Okay? So yet, all of these on the top, with the exception these we didn't really manipulate. Okay? Those we didn't manipulate. We graphically obtained those because we could use our technology to do that. Okay? So what we're going to do here is, I don't think I have any more on this page. We're gonna move along here, and we are gonna say suppose. So what we're gonna do is we're gonna dive into L'Hopital's rule here, okay? And I can cover up this bottom. Envision you don't see the bottom. But so what we're looking at here is we're gonna say suppose, okay, the limit as x approaches a of f of x over g of x produces my indeterminate form of 0 over 0. Well, what does that mean? Well, remember, we're substituting in. So that means when we substituted a in for x, f of a is the same as f of g of a, excuse me, both of those equaled 0, okay, because we reproduced 0 over 0. So then what we're going to do is we are going to take this limit and we are going to say the limit, we're going to take this guy down here, and we're going to algebraically manipulate this a little bit because L'Hopital is a huge application, shortcut for us to do a limit. And it's used whenever we run into specific indeterminate forms of a limit, which the first one is 0 over 0. Anytime we substitute into a limit and we get that value, it's going to be L'Hopital's rule to the rescue, and you're going to see how easy it is, okay? So what we're going to do is, you're not going to understand the algebra going on here, but just remember there's numerous legal manipulations to any equation or expression. Okay, so what we're going to do is I'm going to say, if I have this original one, the limit as x approaches a of f of x over g of x, what I'm going to do is I'm going to manipulate this a little bit, and you're not going to know why I'm going to do it, and that's okay. Don't expect you to know why. But I'm going to divide both the numerator and denominator. I'm going to divide both of these by x minus a. So the numerator is going to be f of x over x minus a over g of x over x minus a. And that's legal to do. Okay, if I have a fraction, per se, let's say any fraction, if I divide the numerator and denominator both by the same number, it's going to be the exact same thing, okay, because I can invert and multiply, and I'm going to get f of x over g of x, okay? Now the next thing I'm going to do here is I am going to actually subtract 0, okay? I'm going to use this right up here. I'm going to subtract 0 from both numerators of my fraction. So now I'm going to have the limit as x approaches a of f of x minus f of a, because f of a is 0 over x minus a over g of x minus g of a, because it equals 0, minus g of a, and that's going to be over x minus a. Okay, that's bad a, but it's an a. And then the last thing I'm going to do is I'm going to apply a property of the limit. Well, the limit of a quotient is the quotient of the limits. What are you talking about? Well, that is the limit of this quotient right here is the limit as x approaches a of f of x minus f of a over x minus a divided by the limit as x approaches a of g of x minus g of a over x minus a, okay? So the limit of a quotient is the quotient of the limits. And what does this produce? Well, you probably are like, yeah, I don't know, I haven't done limits for a long time, but this right here and this right here, they are very, very special things. And if you look at them, bottom line, your first look at them, hey, f of x minus f of a over x minus a. Hey, that's the slope of a line, isn't it? That's just the slope between 2 points. Ooh, I didn't want to use that color. It's just a slope between 2 points, so it's a slope. Well, as soon as I apply this limit notion to it, it's the slope of it's the slope between 2 points that are ridiculously close to each other. And what is the slope in this class? Well, the slope in this class equals what? It's the derivative, isn't it? This is actually right here. That's the alternative form of the derivative. It's the derivative at a specific point. It's the derivative of f. So the numerator is actually f prime of a over g prime of a. The numerator is the derivative at a point, and the denominator is a derivative at a point as well. The point is the same because they're both approaching a. Okay, so big thing here, what is it? This is huge news, people. This is huge. It's the derivative. So that means if I take the limit as x approaches a of f of x over g of x, and it produces an indeterminate form of 0 over 0, and that's the exact same as saying what's f prime of a over g prime of a. And if you're like, what? I don't understand that. Well, hey, come back here. Hey, this right here, that produced me 0 over 0, isn't it? Right? Well, L'Hopital's rule says I can take the limit as x approaches 1 of the derivative of the top, which is going to be 2x, that's like my f. The derivative of the bottom is 1, and then I can reevaluate this limit and plug it in, and I get 2 over 1, and it's 2, my limit. Boom. I didn't even have to factor it. Okay, L'Hopital's rule says if you get this indeterminate form of 0 over 0, we are not going to take the derivative of this as a quotient. It's just going to be the derivative of the top over the derivative of the bottom. Try the limit again and see if it evaluates. Same thing right here. The second one, this is the limit as x approaches 0. See how I got my indeterminate form of 0 over 0? What is the derivative of the sine x? Derivative of sine is cosine x over, what's the derivative of x? It's 1. Okay, so I have f prime over g prime. Let's reevaluate it. What's the cosine of 0? Cosine of 0 is 1 over 1 equals 1. There's my limit. And I don't have to have it memorized anymore. I can use L'Hopital's rule. This last one here, again, I got 0 over 0. So I can say this equals the limit as x approaches 0 of, well, the derivative of 1 is gone. The derivative of negative cosine, derivative of cosine is negative sine, so that's going to give me a sine x on the numerator with a 1 in the denominator. Now I'm going to try my limit again. The sine of 0 is 0 over 1. Anything 0 over anything other than 0 is 0, and I have it. I don't even need graphing technology to get that. Okay? So that's the special thing of L'Hopital's rule. So the first form of L'Hopital's rule, okay, suppose f of a equals g of a equals 0. So basically that's saying when I take that value and I substitute it into my function and I get 0 over 0, okay, that f prime of a and g prime of a exist and that g prime of a is unequal to 0. Bottom line, this is saying, hey, if I evaluate this limit and I get 0 over 0, it actually equals f prime at a over g prime at a. It says take the derivative and evaluate over again is really what it means, okay? So we're going to come here, take it a step further. Well, if I take this a step further, now how far do we want to go? Suppose f prime and g prime are continuous, which is important, because if they're not continuous, they can't be differentiable. And the limit as x approaches a of f prime of x equals f prime of a. Okay? And the limit of g prime of x equals g prime of a. Then the limit of f of x over g of x, okay, when you get indeterminate form of 0 over 0, very important right here. So when I evaluate this limit, if I get 0 over 0, that equals f prime of a over g prime of a. So as I keep going, basically this is telling me right here, substitution works to evaluate my limit. I'm continuous and differentiable because if I plug my limit in here, it's going to equal f prime of a. And the same thing over here. Okay? All I'm going to do is I'm going to say, hey, f prime of a, that equals the limit, okay, the limit as x approaches a of f prime of x over g prime of a. I can use substitution here. That's the limit as x approaches a of g prime of x. Well, if I take the limit of the quotients, okay, that means I can use a property of limits here. I can back this little rascal up and I can say this is the limit as x approaches a of f prime of x divided by g prime of x. Okay, what does that mean? That means this is equivalent to here, They are the same thing. But only when I get an indeterminate form of 0 over 0. Okay? So that's where we're running along here with L'Hopital's rule. Bottom line in a nutshell, L'Hopital's rule says when you first evaluate and you get the indeterminate form of 0 over 0, take the derivative of the top, take the derivative of the bottom, and try substituting that in again and see if you get your limit to exist. As long as you get a limit, as long as you get 0 over 0, derivative of the top, derivative of the bottom, try it all over again and see if your limit evaluates. If it doesn't and you get 0 over 0 again, take the derivative of the top again, derivative of the bottom again, and try again when you reevaluate it, all right? And stronger form of L'Hopital's rule, bottom line, I'm not going to go into all this. It really means that if I have the limit as x approaches a of f of x divided by g of x, just something over something, okay? And furthermore, when I use my original substitution, I get 0 over 0, okay? It's going to equal the limit as x approaches a of f prime of x divided by g prime of x, okay? And I can plug them in, and then I take the derivative of top, bottom, then I reevaluate, okay? And all this statement down here, it's also true in the case for one-sided limits. One-sided limits here and here. X doesn't have to be approaching a finite value. It can be going to positive or negative infinity. It doesn't matter what x is approaching. You get this indeterminate form. You take the derivative of the top and the bottom, and you reevaluate, okay? So we're rolling along here. Example. I already did this one in the beginning again because, see, we plugged it in. We got 0 over 0. We're like, oh, okay. Well, let's look at it as the limit as x approaches 1. Derivative of the top is 2x. Derivative of the bottom is 1. I'm going to reevaluate. I get 2 over 1. I get 2. It's actually a lot easier than having to try to factor that thing, okay? Again, I did number 2 already, but if I plug it in, the sine of 0 is 0 over 0. This is an indeterminate form. This is special with limits. Remember, that means the limit exists. Please find it. There is a hole in my function, dear Liza. And if I get 0 over 0, this says, okay, let's take the limit as x approaches 0 of the derivative of sine is cosine, and the derivative of the bottom is 1. Notice again, I didn't do that as a quotient because the numerator is not a quotient. And then I reevaluate. The cosine of 0 is 1 over 1. That derivative is 1. Okay? Now, a whole new one here. Now we're looking at a new one. The limit as x approaches 0 of e to the x minus 1 over sine x. So I need to plug it in. What is e to the 0 minus 1 over the sine of 0? Well, e to the 0, anything to the power of 0, is 1. Sine of 0 is 0. So yes, I get my indeterminate form of 0 over 0. Therefore, L'Hopital's rule will apply. Notice, you can't algebraically manipulate that thing. There's no way to factor it out. And if you don't have a calculator to graph the limit, what are you going to do? It's L'Hopital to the rescue. It's going to be limit as x approaches 0. Now, here's where I'm not going to spend all my time in this video going over derivatives that you're supposed to know already. What is the derivative of e to the x? Oh, it's e to the x times the derivative of the exponent, which would be 1, minus the derivative of 1 is 0 over the derivative of sine x is cosine x. And then I try it again, and I get e to the 0 over cosine of 0 is 1. That gives me e to the 0 is 1 over 1. This limit is 1 using L'Hopital's rule, okay? I said I'm not going to go over the limits, but anytime d dx of e to the u, remember, where u is a function of x, it's going to equal e to the u times the derivative of the exponent with the chain rule, okay? So here I have the limit as x approaches 1. of Lx or ln x over 2x minus 2? Well, I got to originally substitute. Okay, please don't just start taking derivatives of the top and the bottom, because if you don't get 0 over 0, L'Hopital's rule will fail and you will get it wrong. You have to say, what is the ln of 1 divided by, oh, that's going to be 2 minus 2. ln of 1 is 0 over 0. L'Hopital's rule applies. So now I need to say, what is the limit as x approaches 1 of? What is the derivative of ln x? Well, d dx of ln u, remember, it is 1 over u times u prime. Okay? It's the derivative of my something over my something. And then the derivative of my bottom is 2. I don't even have to simplify this thing. I can plug my 1 in. Well, the numerator, 1 over 1, that's 1 over 2. Looks like my limit is a half. All right? And moving right along, number 5. And number 5 is going to say, well, now I got to plug it in. So that's going to be 0 minus the sine of 0 is 0 over 0. Oh, boy. So I get 0 over 0. L'Hopital's rule applies. So I need the limit as x approaches 0. Well, the derivative of my top, well, that's going to be 2 minus, derivative of sine is cosine, so that's 2 cosine x all over 3x squared. Well, try it again. Well, now I get 2 minus cosine of 0 is 1 times 2. It's 2 minus 2 over plug a 0. I get a 0. Holy smokes, I get indeterminate form again. What do? Apply L'Hopital's rule again. And then the derivative of the top, well, the derivative of 2, that's constant. Derivative of cosine is negative sine. So this is going to turn into 2 sine x over 6x. Okay, let's reevaluate it again. Plug 0 in. Sine of 0 is 0 times 2 is 0 over 0. Indeterminate form again. What does that mean? Apply L'Hopital's rule again. And hopefully you see derivative of sine is cosine. I get 2 cosine x over 6. Now I reevaluate this again. Well, when I plug 0 in, the cosine of 0 is 1 times 2 is 2. Not getting 0 in the top anymore. Over 6 equals a third. Hey, my limit's a third. I could go over this 100 times. And any time I get indeterminate form of 0 over 0, take the derivative of the top, the derivative of the bottom, try it again. And you keep doing that until it evaluates. Remember, 0 over any number. 0 divided by something is nothing. And also remember, something divided by 0, that is not indeterminate. That is not indeterminate. This does not exist. The limit does not exist. No limit. Okay? Only 0 over 0 is your indeterminate form of your limit right now. Okay? So we got one more here for you to do. And actually, number 5, that's an old AP multiple choice question. Number 6 is a 2016 multiple choice question again, applying L'Hopital's rule. So if I plug in here, when I plug 0 in, I get e to the negative 1 minus e to the negative 1 over 0. The same thing minus the same thing is 0 over 0. L'Hopital's rule applies. So I'm going to say limit as x goes to 0. I'm going to take the derivative of the top. Well, that's going to be e to the negative 1 minus x times the derivative of that exponent, which is negative 1, minus e to the negative 1. Please don't freak out. That's a constant. It's gone, divided by 1. And now I'm going to evaluate. See, I have no function at the bottom. I know it's going to work. So now I'm getting e to the negative 1 times negative 1 over 1. That's negative e to the negative 1. And then when you looked at your choices, you're like, whoa, that choice wasn't there.
I need to remember this is equivalent to negative 1 over e. That would have been the choice for it. So you always got to look for equivalence, okay? And what we're going to do is we're going to go L'Hopital's rule for indeterminate forms of negative infinity to infinity. All that means is not only is 0 over 0 an indeterminate form, okay, so is any form of infinity over infinity. So if you ever run into that, L'Hopital's rule applies. If you ever run into this, L'Hopital's rule applies. If you ever run into this, L'Hopital's rule applies. If you ever run into this, L'Hopital's rule applies. If you ever run into this, L'Hopital's rule applies. Any form of infinity over infinity or 0 over 0, those were the ones that made us hunt more and look for the limit and find it, okay? And it just, all it means is it works for, again, this just means it works for one-sided limits. It works as x goes to infinity. It doesn't matter. These are your indeterminate forms that you need to know for this class. If you take Calc 2, there are more indeterminate forms than this, and you will apply L'Hopital's rule to a deeper depth of knowledge, okay? So, example. I'm going to do a few more examples here, and then once these examples are done, I'm done, and your homework will actually be the very last sheet. I think there's 9 problems on there. Those will be your homework problems for L'Hopital's rule. So, as I come along here, now I'm going to an infinite limit. Those are end behavior limits, right? We are horizontal asymptote hunting here. And anybody know what the parent graph of x squared over e to the x looks like? Because if you did, you can probably find your end behaviors. But I don't. But I know infinity squared is going to give me infinity. E to the infinity is going to give me, excuse me, infinity. L'Hopital's rule applies. So I'm going to change this to the limit as x approaches infinity. I'm going to take the derivative of the top, which is 2x. I'm going to take the derivative of the bottom, which is e to the something. The derivative of e to the something is going to be e to the something times the derivative of the something. It's 1 in this case. Then I'm going to reevaluate. Well, 2 times infinity gives me infinity. E to the infinity still gives me infinity. Apply L'Hopital's rule again. It's going to be the limit as x approaches infinity of the derivative of 2x is 2. The derivative of e to the x is e to the x. And see how my function's gone in the top. So the limit is going to be 2 over infinity. What is 2 over infinity? What is 2 over really, really big? 2 over really, really big is really, really small. That limit is approaching 0, okay? Now, I want you to understand, it doesn't matter. It doesn't matter how big the top is. I'm just going to get rid of this for a second, okay? It really doesn't matter. If I had the limit as x approaches infinity over x to the power of 100 divided by e to the x, if you think about this, I am going to have to take 100 derivatives of this thing. Anytime there's still an x in the numerator, because I'm going after an infinite limit, I'm going to have an infinity in the numerator. E to the infinity is always going to be infinity. This is actually going to evaluate to 100. It's not an exciting 100. That's 100 factorial over e to the x. Now, 100 factorial is a ginormous number, but it's still peanuts when it's compared to e raised to the power of infinity. It is a constant divided by infinity. It's still going to be 0 in this particular case, all right? How did you get that to be 100 factorial? Well, if you really want to see, I'll show you, okay? I'm going to have to take all kinds of derivatives. Well, the first derivative of that, that's 100 x to the 99. And if I keep it separated, the next one is going to be 100 times 99 x to the 98. And if I have to do it again, it's 100 times 99 times 98
x to the 97, all the way until I get rid of my x. It's 100 factorial because there's not a function on here. If it were 3x to the 100, it would really be 3 times 100 factorial. It's still ginormous. It's still constant. It would still be 0 in this case. Okay? Next one. Well, if you're forgetting, a rational function. If you're remembering, oh yeah, I remember if the powers are equal in the top and the bottom, it's the coefficient over the coefficient. I know this thing better be 2/5. But if you forgot that, like I know most people do, because it's an infinite limit, I'm horizontal asymptote hunting, okay? As I'm going through here, regardless, I'm taking I'm plugging infinity in here and here, and I get infinity over, infinity. Yeah, there's more infinities in the top and bottom, but it's infinity over infinity. So this is going to give me the limit as x goes to infinity. And when I take that limit, that's going to be 4x plus 3 over 10x. I'm going to apply it again. Guess what? We're getting infinity over infinity again. So we're going to say limit x goes to infinity. We're going to apply L'Hopital's again. We're going to get 4 over 10. The limit as I approach infinity equals 4 over 10, which is 2 over 5. And because it's a rational function, you don't have to show that work, especially if it's multiple choice. Okay, I showed a couple different techniques to find that limit when we hit them, but L'Hopital rule to the rescue. If I hit an indeterminate form, derivative of the top over derivative of the bottom, reevaluate. Okay, another one here. So now, e to the 7e to the x, that looks like a big fat infinity over a big fat infinity there too, doesn't it? Well, so that's the limit as x goes to infinity. That's going to be 7e to the x, that's 7e to the x over 200x. Well, hopefully by now you're already looking, hey man, I got to do this again because I can see infinity over infinity. And I'm just going to differentiate until I know it's going away. And this is still 7e to the x over, that's going to be 200. Okay, now when I plug this in, this is going to give me infinity over 200. What is really big over constant? Really big over constant. My limit's infinity. And if that were not even a choice for your multiple choice selection on a multiple choice test, remember, if your limit's infinity, that really means it does not exist because infinity is not a finite number. So if that wasn't your choice on a multiple choice, that would be your choice. Remember, it's showing the direction of the function that it's going. Okay? Another one here. What is the limit of this? Oh boy. Now I need to know. I don't know what the natural log of infinity is. Well, if you know what your natural log graph looks like, you're going to know as x goes to infinity, the ln x goes to infinity over infinity. L'Hopital's rule, indeterminate form, is going to be the limit at limit at lim x goes to infinity. The derivative of ln x, it's the derivative of my stuff over derivative of x is 1. Well, this is going to give me what? This is going to give me 1 over infinity over 1. Something divided, that's really 0 over 1, is it not? Anything? Oh, that limit is 0. And you can graph them to check them, but that limit is going to be 0 on that one. Here's my very last one. Okay, this is a nice, this would be a nice AP type question too. And because it's an infinite limit, what we really need to think about is, yeah, there's a square root in there, big whoop. But as I plug infinity in here and infinity in here, is that 2? Is that adding of 2 really going to change the number underneath that square root? And the answer to that question is no. I'm really kind of looking at the limit as x goes to infinity. I'm really looking at my big shooters. Remember, my biggest powers only. Everything else is going to go away. Over this -1, really not going to be there. I'm really looking, again, at my big shooters. And then I can look at this as the limit as x goes to infinity. Ooh, do I know what the square root of 16x to the 6th is? That's like a 4x cubed, isn't it? Over a 5x cubed. And then I'm like, whoa, this is kind of weird. Those reduce. It's really the limit as x goes to infinity of 4 over 5. So this limit is going to be 4/5 in the end. It's probably never going to reach it, but that's my limit, okay? And the only reason I could throw this +2 and this -1 out is because this was an infinite limit. If x were approaching like 6 or something like that, totally different scenario. I can't disregard the +2 and the -1 because if x is much smaller like that, the smaller x is, the more that 2 and 1 will affect it. But because it's an infinite limit, I'm going to picture it just like that, okay? Sorry for the length of this, but I'm setting you guys free tomorrow on Friday, and you're also free on Monday. And I'm going to have some type of review for you on Tuesday for our test on Wednesday. And the test will cover 4.5, 4.6, and 8.2. So have a nice weekend, and I'll probably see some of you at Conflict Res on Friday.